Okay, so just a few announcements before we begin. We are going to start part 3 today on simple regression. That's just looking at the relationship between two variables. We're going to move on and look at multiple regression later. That's when you have more than one predictor variable. So now we're just going to be looking at simple regression today and just descriptive statistics on it, not doing any inferential statistics. That will come on Thursday. So the homework is posted. That's due tomorrow, and that's just 2 questions. One is on what we did last time about experiments versus observational studies and confounding. And this next one is on just simple calculations of basically calculating the regression line for simple regression. And we're going to go over that today. So chapters 5 and 8. And then also I want to show you that there's a bonus R problem posted now. So I strongly recommend that you do it. It's fun. It looks at old survey data, and you learn how to make plots of the data. So it's just, you don't need any prior computer experience, and I think it's very useful. So go ahead and try that. It shouldn't take you very long. Just give yourself, I'd say, an hour. It's just basically following directions and downloading RStudio. But that is bonus. You do not have to do that. And then there's going to be a new survey posted, and we're going to look at our our survey data from survey 1, and then I posted a new survey data that's particularly designed to get correlations between, because that's what we're looking at now, correlations between 2 variables. So we're going to look at our own data and look at the regression line in our own data and make predictions using our own data. So that's what bonus survey 2 is about, but I haven't yet posted it, so I'll post that by the end of today. Everything else is up now. Okay, so why don't we just go back to the notebook and finish off where we left off. So let's do that right now. And this one, so I said before to just read pages 23 through 28 because it's just explanations. It's more or less philosophy as related to statistics, what the meaning of causation is. So I think it's very important to be clear about what we mean when we talk about causation in statistics. So basically, so we're on page 23 now, and so I'm going to, first of all, let's distinguish between making predictions and finding causes. When we look at data, like there's 2 very different things we can do, both extremely useful. One is making a prediction. We want to know, if we know X, we want to predict what Y is likely to be. And one is finding causes, okay? So for predictions, for example, you might want to predict, you might want your doctor to tell you what your prognosis is. I'm sure you would. You want it so you can prepare. Or you want to know predict what your finances are so you can prepare for that, right? But let's say you not only want to prepare, but you might want to change that outcome. You might want to increase your finances, right? You might want to change your prognosis. If the doctor gives you a diagnosis of cancer, I mean, you certainly want to know that, but you also want to know what you can do to change your outcome. So that involves finding a cause. So what we mean by cause is being able to change, if you know, changing X, knowing how to change X to change Y, right? So, and they're 2 very different things. I mean, often they're opposite. For example, a fancy car is a good predictor of somebody being rich, right? If they have a fancy car, it's a good predictor they're rich. But that doesn't mean we should tell people to go out and buy a fancy car, go out and buy a Rolls Royce or a Telus. That will help you get rich. In fact, it will do the opposite, right? And if you didn't buy a car, you'll save money. So you may choose to do an action that will save you some money, even though it's negatively correlated with wealth, right? You may decide not to buy a car, because that choice will save you money, even though car ownership is positively correlated with wealth. So they're very important to distinguish those two things. Okay, so let's just make that really clear. And the reason people really care about causation is because then if you find a cause, then you can figure out what things need to be changed to change those predictions, to how you can improve your situation. Okay, so so basically, correlation and causation are, I'm sure you've heard correlation does not imply causation. They're not the same. Here's a good example, just considering health and wealth, right? Those are correlated. So you might want to ask, healthy people are wealthier and vice versa. So that can help you make a prediction. If you know somebody's wealth, you can predict they're healthier and vice versa. But does health cause wealth? For example, because if you have your health, you're able to have a more continuous and successful career. Or does wealth cause health, for example, by allowing you to have more, a healthier diet, more opportunities to exercise, better medical care, etc. Or does some other factor, like I like to think knowledge or understanding statistics, is that something that can cause both, right? Making it look like a confounder. So I think that all of those can be true. Causal pathways can be, very go in different directions, and those all can be true. But we need other types of data to decide this besides just looking at the correlation. Okay, and we saw last time that randomized experiments is what allows you to conclude causation. But you can't always do a randomized experiment. For example, could you do a randomized experiment to get at this? What would you do? You'd have to take people who aren't, randomly make people sick or something, and then see if their wealth goes down, or randomly, how can you do that? How can you get at that? So can you think of any randomized experiments we could do to look at any of these? Can you randomly assign people to be rich or not rich? No, I mean, it's very hard to think of a randomized experiment to get at the relationship between health and wealth, right? It's extremely, I mean, look, we can't even do a randomized experiment on education here because students would really object to it. I wanted to. I thought at first, can we do a randomized experiment and randomly assign people to online versus the in-person class? It would be really simple then. We'd get very clear-cut results, and if the outcomes were different in the two groups, then we could attribute it to the teaching method, because everything else would be the same within random error, right? There'd be no systematic differences. As it is, but we can't even do that, even though it seems like on a small scale we should be able to do that. But with something like health and wealth, it's almost impossible. So then what do? You look for natural experiments that mimic randomized experiments that could be used to check. So can you think of any random changes in health that just occur that could be used to check if wealth increases health? Like, can you think of something that occurs anytime people randomly get rich? That could be sort of a natural experiment. Yes?
Someone wins the lottery?
Exactly. If somebody wins the lottery, like the people who win the lottery, they all start out, at the same level, within random error of health, and then if they become rich, does their wealth improve their health? So that's a great example. So yes, the lottery. So lottery winners randomly get wealthy. But do they also get healthier? Does that improve their health? So does that random wealth, does their wealth improve their health compared to people who don't win the lottery? Does their weight, does their wealth improve their health? And that's a good question. I don't think it's been looked into. How about in the other direction? When do people randomly, that's a harder thing to figure out. Like when random changes just happen to their health, because there's usually it's very difficult to get at this one, I think. I mean, one thing, yes, go ahead. Like a what? They get healthier, so they get wealthier. But do they get wealthier because they get healthier? They're an athlete first, and they're making a lot of money, right? Do you think the ones that stay healthy, do you think that, I'm not sure, because, yeah, athletes that stay healthy get wealthier because they can play more. But that's sort of, it's not random. Maybe because they're playing and given those opportunities, they want to improve their health. I mean, lots of people who are naturally athletic, when they're given that opportunity with the wealth, then they're going to get themselves healthier. So it's confounded. It's hard. I mean, it's hard to see which direction it goes in. It's a great idea, though. I mean, it's hard when you think about anything. It's very difficult to separate it out. That's why randomized experiments are so amazing, because it's very hard to think of natural experiments that mimic them. And one thing that I thought of is, let's say you have identical twins, and one of them just gets some kind of random illness. They're raised, all the other conditions are the same. Then do they lose their wealth? They probably do lose their income and so forth. Yeah, that's the only thing I could think of. So this is hard. So you could say, maybe it isn't so though, because they have. Maybe look at identical twins, right? If one, let's say, one sometimes does get sick. If one gets sick and the other one remains healthy, does that twin lose wealth? Maybe not. Maybe it's a lot of inherited wealth. Okay, so it's difficult to get at. So, all right. Let's see. Let's see what else we want to talk about. Okay, so what exactly do we mean by causation? We have to be pretty clear about it, okay? Because people love to argue about what causes what. And what do we mean when we say A causes B? So in statistics, what we're talking about is if you could change A without directly changing anything else, would B become more or less probable? And then if the answer is yes, then we can say that A is the cause of B. That's what we're going to, okay? And it's not like there's necessarily a single cause of an event. It's just, do you change the probability? If you change A without changing anything else, will that change the probability of making B more or less probable? So let's do our example with, can we say that being female, we saw that there's a negative correlation between your shoe size and how many pairs of shoes you own. And we saw that that was kind of a bogus correlation. It disappeared once we separated into males and females. So gender was a confounder there. And then we saw within either, so basically it was, you can say that it was your gender causing both people to have more shoes and smaller feet. So, so can we say that female gender causes people to own more shoes. What do I even mean by that? That sounds ridiculous. Do I mean there's some particular, it's just because of the biological, it's inherent in female biology to buy more shoes? No, I don't mean that at all. I just mean that that being female happened first, right? Before people bought shoes. You're born a female before you go out and buy shoes. So one thing about causation, if A causes B, A has to occur prior in time, right? And we can think of it this way. Gender is almost always set before shoe ownership. I put that almost in just recently because people are changing their gender now, but that doesn't apply to the data that we're seeing. We're just seeing people who we don't have a lot of transgenders, people who became female and then went out and bought more shoes, right? So gender's almost always set prior. So that, and so that's going to, female gender causes people. So owning more shoes, does that cause people to be female? No. So we have this female cause owning more shoes. Does owning more shoes cause female? So this is eliminated. Or is there some third factor that causes both femaleness and shoe ownership, right? First of all, I should explain more here. So what do I mean by this? I mean, it's like, in all the data that we've seen, at least in Stat 100, females, on the average, own more shoes than males. But there's a long causal pathway between being female and owning shoes that's clearly culturally and historically specific. That's not true everywhere. I mean, I'm sure you've heard of, the phrase, let's keep them barefoot and pregnant. Historically, even in this country, females owned less shoes because they were poor and the men they bought more shoes for themselves and they wanted to keep the women at home. So it's not true. I just mean that it's a long pathway that's culturally and historically specific in this country. But gender came first and then the shoes. That's all I mean. Okay, so I should say that. There's a long causal pathway with a lot of causal links that's culturally and historically specific. I'll just say that's culture specific. And I go into that on the next page if you want to read about that, but so now we know that, okay. Now, owning more shoes causes people to become female? No. And then, what about some other unknown factors that could cause both femaleness and shoe ownership? Well, what causes you to be female? What causes you to be female is just what random sperm happened to hook up with the egg, right? So that's not going to have anything to do with shoe ownership, right? So, whatever determines biological gender, which sperm wins a race, is almost entirely accidental. And it's unrelated to anything that would influence your taste in apparel. There's certainly unknown factors that influence both of them, but they aren't the same factors. Whatever determines sex is not going to be the same thing that determines how many pairs of shoes you own. So we can eliminate this one. And so that leaves only one, right, this one, but it doesn't tell us what sort of causal links on the path. It doesn't tell us, for example, how much depends on social customs and how much depends on hormonal stuff. It doesn't tell us any of that. This is the only one that's left. So we say it's causal. Okay? That's all. All right, so let's see what else we want to talk about. So as I said before, if you're interested, if you're in this further and interested in you can read the rest of it. But for now, let's just skip to here, to page 27. And what are we saying? We're saying that causes always happen before the effects. So if A causes B, it has to happen first. Okay? It always happens first. And then we also, when we want to find a cause, we also have to know something about what sort of confounders are realistic. We have to have some outside knowledge. And I know a lot of you are used to just doing, statistics all being about mathematical formulas and completely objective. But if you really want to find confounders, you're going to have to know some other outside information about the data. You're going to have to know your data inside out. You can't just look from the outside and say and figure it out just from, as we said, from a significance test or just from the patterns. You won't be able to determine that. You're going to have to bring in some outside information. So statistics is almost as much of an art as it is a science. And it's easier to teach it as a math course. I taught in the math department for years, and it's much easier to teach math courses because they're it's just basically a set of rules. But it's a lot harder to teach something like physics, probably, because then you're applying math to the real world, and students have a harder time understanding that. So statistics is the equivalent. It's applying. It's even more difficult because it's not only it's applying math, not just to the natural world, but to everything, to all the things that we want to understand, to human behavior, to economics, to everything. Medicine, every single subject. And so it's even more of a art than a science. So you have to make a lot of probabilistic decisions along the way. All right? And you have to know a lot more about your data, which is why our survey data is the best place to start, because you know it inside out. So you can actually, and you know why people might answer what they did, so you can actually do a lot better statistics on it than you could on some data set that's just handed to you. You know how the data was collected, you know all the variables involved, why we might see these confounders. And that's why it was easy for you to determine that when you looked at the data on shoes, it was easy for you because you had some outside information. You know that women are more likely to buy shoes. If you didn't know that, if you're just looking at some data set, the way I learned stats, it was just, we had no hope to do that. So the only way that, our data is very important in making you real data scientists. Unless you're just interested in finding patterns. But if you're interested in actually finding causes, then this is extremely important. All right. By the way, speaking of our data, I noticed some of you are not giving realistic answers. You are only cheating. We'll pull it up in a minute. But that's only cheating ourselves. Why do we want fake data? We don't. We want our own. I'll show you what I mean. But some people, not most of you, but a few people are just giving these clearly wrong, silly answers. So we got to get rid of that so that we can, encourage people to just answer honestly so that we can actually engage as real scientists. Okay, so the best way as we saw before is these randomized controlled trials, right? But in many cases, we can only get observational data. So this is when we have to figure out, we always need to know what the sequence, it's hard, but it's not impossible to tease out causation. And that's what we're trying to do. And it's becoming an increasingly important field. I mean, I don't know how many of you are familiar with it, but it's a real hot field now, looking at these causal pathways. So in statistics. So basically, even though, so you try to figure out what could be a possible confounder, but there's always going to be these unmeasured confounders that make it very difficult to conclude causation, and that's why randomized controlled trials are so important. Okay, so I think there's just one last thing I want to talk about, and then we're going to go to part 3. And that is what, two things so far we've talked about causal inference, but we also want to do something else. We don't want to just attribute causation to the particular group that the experiment was done on, but we want to extrapolate to a larger group. So those are two types of inferences, and so far we've just been talking about the causation one. We also have to, if you see a relationship between A and B, would the relationship hold up if you look at a broader population? So we talked about, so there's two types here. So how subjects are assigned to treatment and control group through randomization gets at causation. They can be randomly or non-randomly, right? So this is how we design the experiment once the subjects or the experiment, once the subjects are in the group, we can assign them randomly or non-randomly. And only random will lead to causation. But also, we want to know how subjects are chosen for the experiment to begin with from a larger population. So if we randomly sample from a larger population, so this is how we assign, how the subjects are assigned to the treatment and control groups. And this is how the subjects are chosen, so this is basically has to do with sampling. If they're randomly sampled, then we can also conclude that we can extrapolate to the population from which they were sampled from. So by far, this is the ideal if you randomly choose your subjects from a wider population, and then you randomly select them to be within to treatment and control. But and this is the worst if they're not randomly chosen and then they're not randomly assigned to treatment and control. So basically, though, we can only, let's say most experiments are done with volunteers and they're not randomly sampled from a larger population. So we really, if you want to be very strict about it, we really can only conclude causation and say within this particular group, yes, there is a causal effect if you get significant results. But what people generally do is if they're representative of a wider cross-section, people usually extrapolate to the, like what we're doing with Stat 100 students. We extrapolate to maybe like future semesters. Like with this experiment, we'll think, oh, you guys are going to be like future Stat 100 students will be like you, and so we extrapolate, although it's not completely valid. You have to be very careful. Okay? Does that make sense to people? All right. So now, let's see. Why don't we look at our own data and take a break and just do some iClicker questions, just to get that out and have some fun. And then we'll look at, see if we can look at some correlations in the data that we, in Survey 1. So let's go to the computer, get out your iClickers. And here was the survey you just took. I'll remind you what the questions were. So why don't we look at questions that interest me a lot, like, do you believe there's only one person in the world who's your true love? Or do you think there are many who could be? How many people in the world do you think you could truly love? Let's look at that one first. And suppose you won $1 million and were given the choice to either spend it on yourself or give it away to save the lives of children who would otherwise die of starvation. The more money you gave, the more children would be saved. Let's say each dollar saved a child's life. What percent of the money would you give? All right, so let's pull up the iClickers. And, all right. So I just want you to guess. Of course, you can't get this right or wrong. So just guess here. Just anticipate. Who will believe there are more people they could truly love? Do you think males will believe there are more, females, or about the same? And then we'll look at it. Okay, has everybody answered? I'll just give you a few more seconds and just, all right. And now let's see what you said. All right, so the class believes that males, more people think males, although it's, you know, not that big a difference. Here's what the results are. So let's just see who was right. So let's go to our, so let's go back to the data program, and let's go to the histograms and box plots, and we'll look at that question, love. And what was the categories? One, okay, so here's how it looks for everybody together, and the categories I think were, let's just pull it together. There were 6 categories, so that means you don't think there's anybody in the world you can love, just one. This is a few. This is dozens, hundreds, thousands. There must be one more category, right? Let me just see. Isn't there? I'm just curious, sorry. What was it? None. There should be 7, right? 7. So now let's go back to our data program and to our histogram. And yeah, okay, so this is none, one, a few, dozens, hundreds, thousands, and millions. All right, now let's split on males and females and see what it looks like. I haven't looked at this yet. So it looks like most females think a few, and most males think a few too, but there's a lot more males who answered in the hundreds and thousands and even millions. That's optimistic, millions. You'll be sure to find your true love, right? If there's just a few, you hope they live around, you know, what's the chance? What if they live somewhere halfway around the world? We'll never meet them. Okay, so let's look at the statistics and think. So, yep, males generally did. Their average is higher, even though the median was 2 for both, the average is higher. So those who answered males had a good, yeah, you anticipated correctly, and the standard deviation is a lot bigger. All right, the next one we can look at is on the iClicker. Let's look at that. Let's just do this next one. Okay, so we'll start it. Who's going to be more generous? Males or females? That was how much money you'd give away to save the lives of children who would otherwise die. Sometimes results, I'm not sure. This class looks a little different than classes I've seen in the past. All right, so I'm going to stop it and see what you said. Okay, let's see. Female's more generous. That's pretty, hardly anybody thinks male's going to be more generous. All right, and there's a lot of men in here. All right, so let's look and see what you said and get rid of this, see what you actually did. All right, and so now we're going to switch from that to charity. So this is males, and this is females. Look, a lot. We need more bins, though. We need more bins because does that look good? Boy, a lot more men said 100%, but a lot more said 0% too, right? They're not going to give a dime away. So it's on either end, so it's hard to tell what the average. Let's look at the stats. So males were more generous on the average. Look at that, 40, almost 47 versus 45.5 for the average amount of money they'd give away. The median was the same, 50. Wow, that's interesting. So we were wrong, stereotyping like that. That's really interesting. Males, you know, one thing that you're going to see is in almost every single characteristic, certainly physical ones. Men have a bigger standard deviation. They're more likely to be at the very low end and the high end in intelligence, at the very low end and high end in everything, weight, height. They have a huge bigger standard deviation. But what's interesting is, and that's been known for a long time in terms of physical characteristics, but what we're discovering, and that has never, I don't think, been talked about, is that in our data, and you'll see this over and over again, the males have a bigger standard deviation on every trait, their opinions, what they think. And this is a clear example of that. They just have more, they're just more spread out, whereas women tend to be more in agreement. So it's interesting. Okay, so, and the last thing that we were going to look at, let's see what else we want to look at here. Well, we should probably, why don't we look at this data, since we're talking about correlation, and see if you think there are any correlations here. I can show you what disappointed me tremendously, and that's that people were lying on their survey data. This never happened before, and just a few of you, just a few. I mean, the vast majority, probably nobody here, but is lying. But if you look at height and weight, look at this. I've never seen this before in any class I've taught, and I think I just want to address this. I hope people are, I doubt whether it's anybody who's here in class now, but people, like for example, this person is saying what? She's almost, I think it's a girl because we can split. There's only a tiny correlation between height and weight. These people here, like for example this one, is saying 94 inches tall. That's almost 8 feet tall. There's no girl in here that's 8 feet tall. And same with this one, or boy. There just isn't. And if they were, they wouldn't weigh less than 100 pounds. I looked at the data and they listed 90. You can look at all the data and I see what comes up. I can't see who said what, but I can see what their other answers are. And they're just joking. I know it's in good fun and it's funny, so we can laugh at them. But the problem is that it corrupts our data. So let's see. So look what happens, and I think it's more girls than boys because look, okay. So we see this correlation, and here's our regression line. We're going to be talking about this in a minute. And then we split the data. There's almost no correlation between height and weight when you look at females. Now what happens when we get rid of these points? What do you think happens? Do you think this correlation is going to go up? Don't you think it's going to get stronger? So why don't we try that? So you can do this, and so it's a good lesson on outliers right here. We can delete a point instead. So let's just do that. And now you can see that, look, you're looking right here at this correlation, 0.07. We delete this, it's going to go up. See? And it's going to, these are all, see how that goes up? These all are nonsensical. They're just people fooling around. Because nobody's going to be that tall and weigh only 90 pounds, right? All right. Almost 7 feet and weigh 90 pounds, no. All right, so that's more typical of what we see. And now we can unsplit the plot. Whoops, they come back. Let's get rid of them. How about these? I've never had so many people do that, and I'm not sure why that happened. Maybe it was just people completing it fast, but let's just not do it again. It's just silly. All right, because it's so annoying for me. I have to go in there and change things. It's annoying to everybody. And how about this? This might be true. These might be okay. We can't tell. They're possible. Okay? So that's what happens if we do delete it, though. It's going to go up. All right. Any questions on this? Okay, and the last thing we were going to, I think that's about it. Why don't we get to the document camera and what we're going to get to right now to part 3. So on page 29, let me just show it to you. Page 29, we're going to be looking at chapter 8 today. We're going to finish this. And this is on scatter plots and regression lines. I'm sure most of you have already had this. But So a scatter plot, like we just looked at, is a graph for showing the relationship between two variables. One variable is assigned as the x, and the other is assigned to the y. And it's kind of arbitrary, but usually you think that the x, we call it the independent variable, and that's somehow, the y is called the dependent variable, and we think that y is somehow dependent on x. So the convention is to call x the independent variable and y the dependent. And usually the independent variable is used to predict the dependent, but not always. So now, this is important. Scatter plots only show whether or not there's an association between two variables. They do not show you whether that association is causal. So basically, you can have these completely accidental, coincidental associations, just pure coincidence. And there's a site where there's a ton of them I was just looking at, and we can look at it now, and they're pure coincidence. So this one is what? This is the number of people. This is the number of people who died by becoming entangled in their bed sheets and the total revenue generated by skiing facilities. And usually they're just shown over time, and they're gotten at by just cherry picking, by just looking at, I mean, you never saw stuff like this in, you never would notice stuff like this, but if now with a huge computer, with huge data banks, computers can search for the same pattern over years. So that's how they come up with these crazy ones. So that's one extreme end, is these accidental associations, right? We can watch a fun video right now if you want, looking at that. And because people like to see the two extremes, that and clear causation, like where smoking causes cancer, right? That, and they like to think of the two extremes, where we're going to spend most of the time looking at things that like health and wealth, where it's much harder to, it's not clearly one way or the other, not clearly completely bogus or clear causation. So here's, let's look at this. So we can watch. This is entertaining. I think it's a fun video. He says a lot of good things.
Correlations. You might have seen.
Okay, here he is.
This is Tyler Vegan, and I'm here to talk about spurious correlations. You might have seen some of my charts based on a program I wrote to find correlations between completely unrelated sets of data. For example, there's a correlation between the divorce rate in Maine and the per capita consumption of margarine in the United States. And there's a correlation between the number of worldwide non-commercial space launches and the number of sociology doctorates awarded in the United States. But what do those mean? Anyone can plainly tell that there's not actually a connection between margarine and marriage. But everyone considered the hypothesis for a split second and said to themselves, are we launching sociologists into space? And that's the part that's so cool. We were scientists, if only for a moment. We saw data, we formed a hypothesis about that data in the form of a causal mechanism, and then we rejected that hypothesis based on our personal experience with the world. That's a big deal, and it's the part that computers can't do. Research is about discovery, but only humans can actually make discoveries, though computers are a great tool. The purpose of the spurious correlations I show is not to say that data is ambiguous, so you can interpret it however you want. No! Statistical data can show correlations, and then it's up to us as rational thinkers to establish whether there's actually a connection between the variables or if it's merely a coincidence. We do this in two ways. First, we need to mathematically prove that a correlation really exists. Scientists have much more sophisticated methods of determining whether two variables really correlate by using p-values and significance. But I am not an expert on statistics or number theory, so I'm not going to talk about that part here. Instead, I'm going to leave that to another YouTuber, like Singing Banana, or Numberphile, or Phi-Heart, to make a video about it. And when they do, I'll link it here. Second, to establish a connection between two variables, we need to establish the Y. The Y is usually called the causal mechanism. The causal mechanism is like the verb in a sentence connecting two things together. For example, there's a correlation between how many videos I've watched by SciShow Space and how much I know about space. The causal mechanism is that Hank and Caitlin are teaching me more about space. The teaching is the verb, and it's causing me to know more about space. Finding causal mechanisms is the key goal of a lot of scientific research, because when we find causal mechanisms, we learn that much more about the world around us. Sometimes we see a correlation that we can't explain, and it might inspire us to search for a potential cause. A good example of correlations leading to conclusions is the connection between smoking and lung cancer. In the early 1900s, the incidence of lung cancer was on the rise, and no one really knew why. Then, in 1929, German physician Fritz Lickent published a paper in which he showed that lung cancer patients were particularly likely to have been smokers. That is, there's a correlation between smoking cigarettes and the incidence of lung cancer. That paper led to a lot of research in which we learned about the dangers of smoking, but it never would have happened if someone hadn't seen the correlation and then researched. To sum up, correlations are a great starting place, but it's up to us to be critical of the correlations that we see. Correlations between two variables could be merely coincidence, or they could be the result of an underlying causal link. And every time we see a correlation, we have the marvelous opportunity to try to figure out which one it is. I'm Tyler Vegan. Have a great day.
Okay, so what I loved about what he said was just that, computers and can only do so much. It's up to us to figure out what's causation, whether X is causing Y, and not just whether they're correlated. But he just examined these coincidences that are just, they're pure coincidences, and they're found by searching massive databases. And it's not like something we'd ever wonder about. It wouldn't come to our attention that two things are correlated. These are sort of just silly and bogus, and they're usually always time dependent. So he talked about that, and then he talked about the smoking and the lung cancer, the clear causation, where we actually have experimental evidence in the lab of the causal mechanism, how smoking does it. We've done experiments on mice and monkeys, and we have massive amounts of data to show that. But most of the action in our class is he sort of ignored how the parts that come up all the time, where you have to think about what the confounder is, he alludes to it back in the 1920s, they just saw this correlation, and took a lot of work to conclude this. In fact, when I first started teaching at this university, the book I was teaching at still thought it wasn't proven. But now, so there's also, I divided up these middle ground here into two cases. The clear confounding, where it's obvious that both variables are caused by a third variable, like the lighter example. Lighter, we saw an association between lighter's and cancer, and we realized pretty obviously that smoking is the confounder. So here's one that probably, if you've ever had an intro stats course before, this is the classic example, that the number of deaths by drowning in ice cream sales, they're correlated. But, the clear confounder is high temperatures. So I'm sure you've seen that, well, maybe you haven't, but this is a very classic example, that if you plot ice cream sales on the x-axis, ice cream sales on the x, and then the number of drowning deaths on the y, you're going to see a positive correlation. When people aren't buying much ice cream, they're not drowning much. When the ice cream sales go up, the drowning goes up. And you're going to see some kind of positive correlation, an upward trend, like this. But obviously, it's the high temperatures. When it's hot outside, when you have high temperatures, when it's hot outside, people are more likely to buy ice cream, so more likely they buy more ice cream in the summer, and they also go swimming more, so they drown more. So that is a clear confounder, all right? And that you might come across without doing these computer searches that are just completely time dependent there. Now let's look at the relation between, often the relation may be causal, but we don't know. like health and wealth. We just talked about that. That's much harder. We see this correlation between health and wealth, but as we saw, we're not sure whether health is causing wealth or wealth is causing health. Probably both of them, right? And there's probably something else, like knowing statistics, right? That's what I said, and other things that are causing both of them. So it's not an either-or situation. It's probably a mixture of all three. All three situations here. All right, so that's the idea. So, so before we go further into looking at this, let's just get to the mechanics of how to get a regression line from a scatter. What a scatter, how to these 5 descriptive statistics that we have on the 2 variables, and let's look at the regression line. Okay, so when you have this scatter plot, when you have an x and a y variable, and you plot them like we could with our exam 1 and exam 2 scores, or height and weight. So that means every person has a pair of numbers associated with them. So you get the scatter plot, and let's say it follows, it looks, so each dot, if we were looking at the data we just looked, each dot, our survey data, each dot would represent one person's answers to 2 quantitative variables, something on the x and the y, like height and weight. So you have that, and then if it follows a linear trend, instead of like a curvy linear trend, like it could follow a curve, but if it follows a basically linear trend like this, and we can fit a straight line through it, then what we can do is we can use this line that we can fit through it as a prediction line, also called the regression line. And it could be our best prediction of y given a particular x variable. Okay, so that could be used to estimate y from x. I can estimate your weight from your height. Okay? It's also called this regression line here. So what does it do? It can be used to, it can be used to estimate the average value of y at each value of x. So it's also called this least, that's what it's doing. And it's also called the least squares line because it's the line that minimizes the distances, like for each individual point, there's going to be an error. Like let's say, you have some x value and we predict this, let's say, but you're way up here. So that's an error. Or you're way down here. So that distance from that line is an error. So it minimizes the, not the average error because there's positive and negative and they'd average out to 0, but that once you square those errors, then the average squared, then it would be it would minimize the squared errors, okay? It minimizes the sum of the squared errors. The vertical distance is the actual y's are from the predicted y's. The predicted y's are along this line, and some people might fall on the line, like this point falls right on the line and has an error of 0, but everyone else has an either positive or negative error. And so we're picking the line that minimizes those sum of those errors. That's why it's called the least squares line. It can be summarized by these 5 statistics. I wrote the average of x, that's the mean of x, the mean of y, the standard deviation of x, the standard deviation of y, and something called the correlation coefficient, which you've probably seen before. Certainly if you were in Stat 100, it's a measure of how close the points hug that line. If they're perfectly on the line, there's a correlation of 1. or -1 if there's a negative correlation if it slips down. If there's no correlation at all, like no correlation at all, so if knowing X tells you nothing about Y and you just have like random scatter, like that, well then the correlation is 0. And your best prediction would just be, let's say the average of X was right there, then for no matter what value, average of Y was right there, then no matter what value of X you were at, we'd predict the average. For example, this would just be R of 0, and it ranges from that to you could have an R of 1 if all the points were on a line, so you could perfectly predict Y from X. That would be R equals 1, and then you know R equals -1 would look like this. Okay. And so an example of this would be like maybe we can look at our data, but probably things like height predicting GPA. However, how tall somebody is has nothing to do so with their GPA, so it wouldn't matter if you were very short or very tall. My best prediction for your GPA would just be the average GPA. All right? And when would there be a perfect correlation? That's when there's a formula relating X to Y. Like here, a perfect negative correlation would be like the number right you got on an exam is going to be perfectly correlated with the number of wrong. If there's 100 questions on the exam, then if you got a 60 right, I know you'd get a 40 wrong, and they'd be opposites. If you got them all right, you get them no wrong, etc. Okay, so that's the idea, and it can range anywhere in between. Now, how is it computed? I'm not going to go into that now, but it is on, if you want to see the actual computation, it's on page, where did I put it? So this is on, to see how R is computed. Basically, what you have to do is you have an X to compute R, you have an X and a Y, right? And they could be in different units completely. Like, let's say X is your height. Well, that could be in pounds. And Y could be your weight. I mean, height wouldn't be in pounds. Height is in inches, and your weight would be in pounds. They're in different units altogether. So what would it, you have to, in order to figure out a correlation, you have to basically change them to standard units. You have to change them to standard units. So if somebody was to z-scores, so if there was a perfect correlation between somebody's height and their weight, then their z-scores would be exactly the same. Because what does it mean to say they're exactly the same if you don't translate it into some measuring stick? So you first translate into z-scores, and then you compute the correlation coefficient as the average product of the z-scores. It's the X, I can show you, page 253. And you've seen this before if you've taken Stat 100. Whoops, it's not 253, sorry. It's 249. So let's switch that. I'm glad I went to look for it. So it's page 249. And it's right here. So it's abbreviated by the Greek letter rho, and it's the average. Once you change the z's and the once you change the x's and the y's to z-scores, standardized scores by subtracting the average and dividing by their standard deviation, so they both have an average of 0 and a standard deviation of 1, then you multiply the z-scores together. And for each person, you'd multiply the z of x times z of y, and then you take the average of that. And that's the correlation coefficient, and here it is in symbols, too, and for sample. The sample, this is one of the few where the sample's the same. So you don't have to worry about that n minus 1. You can just do the same thing. It's explained here. All right, but that's enough digression. That's the correlation coefficient. And now we're back here, and we have something else. Here's an idealized scatter plot. We have something else that's called, that you probably haven't seen unless we're in Stat 100, and that is what we're comparing the regression line to, and that is the standard deviation line. And that is the line where if there was a perfect correlation, every single point would fall on this line. So it's if you translate it to z-scores, this would be zy equals zx. And if you translate it to z-scores, this would be zy equals r times zx. This would be, in z-scores, this would be zy equals r times zx. So when r is equal to 1, those two are the same, 1 or negative 1. These aren't in z-scores here. If they were, you know, that would be the point of averages right there. That would have to be 0, 0. All right, so that's the idea. And this regression line, of course, is always less steep by a factor of r, right? R has to be, unless r is 1, this is going to be less steep. So it's always less steep than ST line, because the slope, r, is always less than or equal to 1. So it's always less than or equal to, less steep than the standard deviation line. Less steep or same. Okay? So basically, when you're in, if you go over one standard deviation in the x direction, like a z-score of 1, let's say, then to get to the regression, to the standard deviation line, you go up a whole standard deviation in the y. And that would be the point in z-scores, that would be the point zx equals 1 and zy equals 1. And this would be zx equals 2, 2, 3, 3, 0, 0, etc. The z-scores are the same. But to get to the regression line, you don't go up a full standard deviation. The slope is only, you know, rise over run is just r. So you go up a fraction of it, and that fraction is r. So for example, since you have like similar triangles here, you can draw, let's draw a bigger triangle. I mean, all of them are going to look the same, and we can estimate what the correlation coefficient would be here. So a flat line right here, let's call that 0, and let's call perfect correlation up here 1. And if you mark this off between 0 and 1, the correlation can run between negative 1, let's just look at positive. The correlation could go between 0 and 1. We can mark it off, so you could say 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, etc. And this looks to me, that estimates to be about 0.5. So in picture, in diagram, r is approximately 0.5 because it's about half as steep. This line is half as steep as that one, if you measure the steepness grade. Okay, now when we're not in z-scores, we have to adjust. When you're not in z-scores, you have to adjust by the standard deviation of y over the standard deviation of x. That's what I'm saying. If you go over one standard deviation in the x direction, you go up only r in the y direction. So that is what the slope of the regression line is. It's r times the standard deviation of x over this. And that is something that won't be given to you, so you need to know that for the exam, because it's really important to think about the relation here. Okay, I'll just write it large. So the slope, just so it'll pop out at you when you're looking over your notes, is equal to what? R times the standard deviation of y over the standard deviation of x. Okay. You need to know that. And something else that we learned okay, so now let's just think about what we're doing here. All right, so we have, let's just look at like a particular x value. We'll make a little strip here, an x here. Just make a little, I'm bad at drawing. So I'm just making a little line here. And there's going to be points in here, right? Now, what the regression line does, this line right here, is it estimates within this vertical strip here, it estimates, for a given x, there's lots of different y's. For a given height, there's lots of different weights. So it estimates the average within each vertical strip. It estimates the mean value of y at each vertical strip. That's not what the SD lines does. That estimates, that tells you exactly, if you were just as, gives you the same ranking in both. If there was a perfect correlation, everybody would be there. All right, but there's scatter around this. There's scatter around the regression line, right? There's errors. The distance a point is off the line is called its residual. And what is the typical, what is the average of all those distances? Like if you took every single point, actual point, and looked at how far it was from its predicted, and averaged them all together, because of the way the regression line is drawn, you'd get 0. Because their positive and negatives would cancel out. That's the way that we made the regression line. So what do? What you usually do in statistics is you square the distances, right? And so basically you want to look at the standard deviation. The spread around this regression line is a good measure of the typical spread around the regression line is this standard deviation of the errors. So the typical error around the regression line, we measure spread in statistics by standard deviation usually. So it's the spread, it's the standard deviation around this is the shortcut formula for it. Instead of looking at every single point, right? Subtracting off its distance from getting that distance, and then squaring it, and then taking the average, and then taking the square root. That's how you take a standard deviation of all those points in the data set. Instead of doing this, we have this shortcut formula for it, which is the same thing. The square root of 1 minus r squared times the standard deviation of y. All right, that's called the root mean square error. It's the same with the standard deviation, right? The square root of the average of the squared errors is the same as the definition of a standard deviation. So that's the root mean square error. If you square it, it's called the mean square error, which comes up a lot in regression analysis. All right, so that's this right here. And I've decided, since you're coming from, that I will give you this on exam. So this will be given to you. So you don't have to memorize it, even though you had to memorize it in Stat 100. Okay, so these are really key statistics. Let me just see how far we have to go. Okay, we can still finish. Okay, so this mean square error and r squared are very key statistics in analysis of variance, which is what we're going to do at the end of this part 3. Because r squared is the proportion of the variation of the y's explained by the regression line, and 1 minus r squared is the proportion left in the scatter around the line. Now we're going to talk about this a lot later, but first let's just get through the mechanics and so you can do the homework. All right, so now what is this standard deviation of the, I'm not proving this, but I want you to remember it. So let's see why it makes sense. So let's see why this formula makes sense. All right, let's just look at the two extreme cases. When r is perfect, when r is equal to plus or minus 1, what would this predict? When r is equal to plus or minus 1, you'd have 1, what would you have? You'd have 1 minus 1 times the standard deviation of y. So you'd have 0, you'd have 1 minus 1 here. So you'd get, so this would imply that the standard deviation of the errors is equal to 0. And of course it is. I'll just look at the positive quadrant here. So when r is equal to 1, as we said, it looks like this. And you have no error. So there's no spread. And when r is equal to negative 1, same thing. So at least it makes sense, the formula, in those two extreme cases. All right? So how about the other case, when r is equal to 0? What do you get then? If r is equal to 0, then you stick a 0 in here. You get the standard deviation of the errors is equal to the standard deviation of y. And let's see if that makes sense. So let's draw a picture, y and x. Here's y, here's x. And when r equals 0, there's no correlation. Knowing x tells you nothing about y, so it's just random points. And our best prediction right here for x, for y, no matter what x is, would be the average y. That's right halfway up there, the average y. And then the spread around that would be the standard deviation of y. The spread around the average is defined as the standard deviation of y. So yes, that works out. So this checks and that checks. All right, now let's quickly do the problems here that you're going to have to do for homework. And I'm sorry I'm running so late. We have 5 minutes to do them, but they're super easy, really. Okay, so now this scatter plot depicts the exam averages and the final exam scores of 100 Stat 100 students from a previous semester. All right, and so we have this regression line here. That's the regression line. And right here is our SD line. Okay, and now, first you want to find the slope. And here's our 5 summary statistics, and we want to find the slope. And the intercept, to find the slope, we just said, you have to remember, is what? It's going to be r, the correlation coefficient, times SDY over SDX. So in this case, there's our correlation, 0.6, and which is y and which is x. Whatever you're predicting is y. So y is the finals, and x is the exams. And so here the standard deviations would be 10.3 over 9.2, and this is 0.67. So you'd put that in here, right? Now we just want the intercept here. So to find the intercept, what are we going to do? We know that the point that we know that's on the line is this point right here of averages, right there. So we could just plug in point of averages, the average of y and the average of x. So for the final, we'll plug in 73.6 is equal to 0.67 times the average exam, which is 83, and then that would be plus the y-intercept. And just solve for the y-intercept. So I got the y-intercept then is equal to 17.99. And I'll round to 18. So there's my equation. That's the regression equation. Okay? So now use the regression equation to predict the final exam score of a student with an average equal to 90. So here's an average equal to 90 right here. So I want to predict, I want to look at that point right there. What is that point? I can estimate it to be in the high 70s, right? But to figure it out exactly, what am I going to do? I'll just plug it into the equation here. So I'll say our predicted y, we call y hat, is equal to 0.67 times 90 plus 18, and I got 78.3. So that's where that point is right there is 78.3. That's our prediction for that person. Any questions so far? What? This is how Stat 100 used to be. I'm not kidding. Before we made it simple and got a notebook, wrote a notebook. These were real. This is when I first came into Stat 100. These were the scores. That's why they called me in. I was in a women's group where people were crying about Stat 100. They said it was the worst. It was so hard. They hated it. And now it's like one of the easiest courses. These were the scores. And now we teach much more. And people think it's too easy. You can make anything a lot easier if you strip away a lot of the jargon and make it understandable. Okay, so now hopefully I'm trying to do that with Stat 200, but we'll see. Okay, do you think that prediction will be exactly correct? No. Look, it's not. Look at all the people who got 90s. There's a range, right? There's people down here. They're all over. It's not exactly correct. We're just making a prediction, right? So no. So we need to add some wiggle room, and that's what that standard deviation of the errors is. So all we have to do is say, okay, so what's that standard deviation of the errors? Also known as the root mean square error. Errors. So that is equal to, remember, the square root of 1 minus r squared times the standard deviation of y. So what's that? The square root of 1 minus 0.6 squared times 10.3. And that is 8.24. So just a crude way, if we want to, so we'd say we'd attach that wiggle room to the estimate, okay? So to give it a range, you want to, instead of giving a point estimate, you want to give a range, right? You want to say, hey, I think the final score is going to be 78.3, give or take. It's real different if you say give or take 0.5 points or if you said give or take 20 points. Well, we're saying give or take about 8.24, which means that you know, that's a range. You subtract 8.24 and add 8.24, and the range then is 70.06 to 86.54. So that's what so that's enough to do the homework for Wednesday. And then we'll look at, we're going to start doing inference for regression.